All right, chapter 20, stellar evolution, as it says here. So, in chapter 19, of course, we already saw stellar evolution, the contraction of a giant cloud into fragments and into hundreds to thousands of stars, protostars that eventually become stars on the main sequence, and where they fall onto the main sequence depends on mass. And remember, that was stages 1 through 7. Remember, stage 7. That's important because this chapter 20, will begin with stage 7, which puts a star clearly on the main sequence. Okay. All right. So So then we start this chapter off with leaving the main sequence. Okay, so here's the thing. Stars like the sun are going to spend, around 10 billion years on the main sequence. We're not spending a lot of time talking about that. It's kind of important because that's the vast majority of the lifetime of the star. All these changes that it went through. To actually become a star, it took millions to billions up to about 1 billion years. Hundreds of millions of years, but once it becomes a main sequence star, it just stays there, right? That's the thing. They want everybody to understand. It just sits there on the main sequence and converts hydrogen into helium, right? And it stays in equilibrium. That's the thing. If at some point in its life, there's some minor fluctuation, the star returns to can make itself return to equilibrium. Remember what equilibrium is all about. Let's move along. So equilibrium is the inward force of gravity and the outward thermal pressure that is so now what is the thermal pressure coming from? The conversion at the core of hydrogen into helium, the fusion process. The fusion process converts hydrogen into helium. That's the nuclear burning. Okay, so and I guess I should say something about that as well. We'll use that terminology, nuclear burning, or the star is burning. It has nothing to do with what we consider burning, on the Earth, right? That's a chemical process involving oxygen, right? This is not when astronomers talk about burning. It's a nuclear process. That's not something you see on Earth. Especially in the fusion, you'd have to have a hydrogen bomb going off to actually witness, hydrogen burning. All right, so that's not something that happens, thank goodness, every day. You wouldn't want that. That would be a really bad situation. All right, so eventually the star will the fuel supply of a star will run out at the core. Okay, when that happens, that's where we're starting. Okay, so the star leaves stage stage 7, the main sequence stage, and goes to become one of the subgiant phase, as we're going to see. All right. Here's another interesting observation that they're talking about here is no one human life is what maybe 75 years, 100 years if you're really lucky. So nobody can ever be around. And in fact, all of recorded human history is not even long enough for us to witness a single star, even the most massive star, going completely through its life cycle. That's just not possible, right? Because you're talking about, with really massive stars, hundreds of millions of years to completely go through their life cycle. For lower mass stars like the sun, or even lower mass, you're talking you're talking billions of years to tens of billions of years, and the really low mass stars, trillions of years, right? So there's no way. Keep in mind the universe itself is 13.8 billion years old. So there are stars that are not even anywhere near. There hasn't been enough time in the age of the universe for those stars to reach this stage. These low mass stars to reach stage 8, as we're going to see. Right, so how do we do this? If we can't watch a single star evolve, what we do is we look at clusters, star clusters. So groups of stars that were born at the same time. So when they were born at the same time, some stars had more mass, some stars had less mass, and so we can see that on the, we look at the star cluster and we look at all those stars on the main sequence, and that will give us a picture of the evolution of stars. All right. So like I mentioned before, any fluctuations during the main sequence, which is called stage 7, that gets restored, right? The star will return to equilibrium. Let's say you had this massive solar flare or something like that. That's going to affect things in a minor way. The star can easily recover from that. That is, remember what equilibrium is. Once again, I know I'm repeating this, but the star, for it to be in equilibrium, the inward force of gravity, which is always there, keep that in mind, that the force of gravity is always there, that has to be matched, so it has to be equal to the outward pressure, which is thermal pressure, which is pushing back. All right. As we'll see, that's not always going to be the situation, right? The gravity's always there, but the outward push due to fusion, which has its source in the conversion of hydrogen into helium, is not always going to be there. So what happens? All right. So as I was kind of leading to, the star will, the core. So remember, we're talking about the core. There's still hydrogen in the star when all this happens, but it's not the hydrogen in the core. So when the core hydrogen runs out, then there's just not enough. There's no more hydrogen to turn into helium. So basically, the core is essentially all helium. Then the star leaves the main sequence. Okay, so, and in fact begins to cool down, expand, as we're going to see. All right. So and the evolution depends on mass. The low mass stars like the sun or lower, they go more or less quietly. That is, their deaths. Actually, more than you can actually have stars up to about, I think, 12 times the mass of the sun. They pretty much go relatively quietly. I mean, there's some, but the ones that are more than 12 times the mass of the sun, we'll talk about that at the end of this chapter, they go out with the most spectacular of all explosions, which is called a supernova explosion. All right. And it's actually a pretty rare thing to have stars that have this 12 times the mass of the sun or more, and then they die. But of course, you just think about our galaxy. There's 200 billion stars, and then there's billions, hundreds of billions of other galaxies out there. And so, as astronomers, we will encounter this kind of thing. Just statistically, right? There's going to be stars that during our lifetimes will die, and we detect that light. We detect that change in the light. All right, so this is basically what we were talking about with the the star in stage 7 is this where most of the core is hydrogen. There's a little bit of helium, about 10% or so, and then here's a star RH, or sorry, the age, not RH, but the age of the sun. So what's happening is there's still hydrogen fuel, but of course for the last 4.5 billion years it's been converting that hydrogen into helium, and so you get where's my mouse? There it is. So you get a good amount of helium at the core. All right, so keep that in mind. But there's still some hydrogen in the core, and then when the star begins, the moment it loses hydrogen and there's no more hydrogen at the core, remember there's still hydrogen, but the hydrogen exists in a shell around the core, but the core is helium. Then the star leaves the main sequence. Okay, so that's where we're heading. So the fuel supply at the core is used up, and now what happens? Remember, gravity is always there, right? So gravity says, hey, there's not as much of a push outward. This outward push due to the fusion of hydrogen and the outward thermal push, which is caused by the conversion of hydrogen into helium. That's just not there anymore, and so the star begins to contract. It gets smaller and smaller, right? All right, so let's see. What happens is because there is fuel, the hydrogen fuel in outside of the core. The core will not the core. The shell that's around the core will actually begin to fuse. It'll be hot enough, right? Because remember, contraction is volume getting smaller. So when if you take a gas, right, which in some senses this is not exactly a gas, it's called plasma, but that's a different story. Anyhow, as it gets smaller, as the volume gets smaller, the temperature goes up, right? So the shell will the atoms of hydrogen will be closer together, and that closeness is just higher temperature, and fusion can begin to occur, or fusion begins to occur in the shell, or the outside of the core. So this is kind of the snapshot of the entire thing. So 7, of course, is the main sequence. Then so this is kind of, we're going to go through these steps in a little bit more detail. The subgiant phase is stage 8. Stage 8 then leads to this what's called a helium flash, when helium first begins to burn in the core. It's got to get hot enough. You got to get a temperature. Let's see, what the temperature I think has to be. What does it have to be? Like 100 million Kelvin or something like that. Anyhow, and then there's what's called the horizontal branch, where the temperature increases but the luminosity does not increase. There's an asymptotic branch, so the star is becoming, it's going from, we'll talk about that. It's actually kind of complicated. And then there's the star gets hot enough to convert helium into carbon. So this is for the low mass stars. Okay, so we're talking about low mass stars here, and then eventually the outer parts of the star, have grown so, because the star is cooling off. The outer parts